Alright class, today we'll be talking about how you can simulate your digital circuits using the basys3 FPGA board and the vivado design suite. Now so far we've talked about how you can design your own digital circuits using Boolean equations, truth tables, and logic gates, and we've even talked a little bit about a hardware description language called VHDL. But so what? We have all these circuit designs on paper. How do we make them do something useful? How do we test that they actually work? Well, one of the ways we can do that is using something called an FPGA, or field programmable gate array. So a field programmable gate array, not to be confused with field programmable Gatorade, the preferred drink of robots and cyborgs at the University of Florida. But a field programmable gate array is essentially a chip, the big chip in the middle of your basys3 development board, that consists of configurable logic blocks as well as interconnect blocks. So these configurable logic blocks that you can see here essentially take in a gate description in VHDL or System Verilog or any other hardware description language and implement the logic in the circuit. Now if you have too much logic for one logic block, then you can connect it up to other logic blocks using this programmable interconnect here. Fortunately, the vivado tool provided by Xilinx, who's the same company that makes our FPGA, automatically does all of this configuration and logic division to different logic blocks for us. So we really don't have to worry too much about the details, and we can just worry about creating our circuit in a high-level language like VHDL. Alright, so let's get to it. Let's create a circuit and put it on our basys3 board. Now, what's the first step of creating a circuit? Well, the first step is to always have a problem. We want to know what we're building. And so for that, I've created a test circuit that we're going to build. So here's what we have to design. Andrew, Jen, and Amy are enrolled in a Cal Poly machining class. As part of the class, they need to go to the machine shop in their spare time to build their projects. Following best safety practices, however, they are only allowed into the shop if at least two of them are present. Remember, never machine alone. Now, design a locking circuit that will grant access to the machine shop if two or more of the three students are present. Alright, our first step will be to draw a black box diagram. So we have our circuit. Let's call it machine room access. Then we have our inputs, Andrew, Amy, Jen, and our output, access granted. If access granted is 1, then the door unlocks. If it's 0, the door stays locked. Alright, now let's actually design this circuit. How do we build something like this? Well, let's go to our Boolean table. Boolean equation. We could easily build a truth table for something like this, but since this is a relatively simple circuit, we can just pull it out using the word problem. So we need access granted to be 1 if 2 or more of the students are in the machine or want access to the machine shop. So just doing the combinations of that, we know access granted is 1 if Andrew and Amy want in, or if Andrew and Jen want in, or if Amy and Jen want in. Now we can also have a fourth term, which is if Andrew and Amy, that should be an and Jen want in. But by looking at this, you can convince yourself that this last term will be satisfied by these three terms. So we can optimize this away and make it nicer to implement in VHDL. Now from this Boolean equation, we could go directly into VHDL. However, since we are specifying hardware, it's always a good idea to sketch out what the circuit should look like in gates. So we will need 3 AND gates, one for each of our min terms, 1, 2, 3, and then an OR gate with 3 inputs to combine them all together. So we have term 1, term 2, or term 1, now term 2, and then term 3, all combined together to give us access granted. Now this step may seem a little redundant for such a simple circuit, but it's always good practice to draw out your expected logic so that way you know what to expect when you get the FPGA implementation. Alright, from here we're ready to enter this into Vivado. So let's pull up Vivado. File, new project, and we're going to create a project. We can call it anything we want, but let's call this video tutorial. And it'll create a project subdirectory for us. Remember to set the project location. If you're using one of the lab computers, be sure not to save it on the C drive, since that gets wiped every day at midnight. Save it on your U drive. Also, make sure there are no spaces in the project name or the file paths, since Vivado doesn't really do well with spaces in the file names. Click Next. Alright, select an RTL project. RTL stands for Register Transfer Language. And that basically means we'll be using some sort of hardware description language in order to specify our circuit. Now we could decide not to specify sources at this time, but we want to create a source file to hold our circuit description. So click Next. Then create file. Alright, file type. In this class, we'll primarily be teaching in VHDL, although Vivado does support things such as system Verilog and regular Verilog. For my students, you're free to use whatever language works best for you, but officially our textbook uses VHDL, and that's what's going to be on the exams. So file name, let's give a name to this. Call it Maxess. And we want to store it in the project directory, so that's fine. Click OK. Next, we don't want to add any IP. We don't want to add constraints at this time either. And now we have to specify our FPGA. So the FPGA on the basys3 is an XC7A, or product or family Arctic 7, and general purpose subfamily Arctic 7. Our package is CPG 236. Alright. And we have an XC7A35T speed grade -1. So we select this chip. Okay, click next, then finish. There we go. Alright, so now once the project opens, it has a nice little window that lets us define the module for that source file that we created. Now it automatically makes the entity name the same as the file name. So since we created the file Maxis, it has the entity name Maxis. And so let's put in our inputs. Andrew, Amy, and Jen. Now we could make these into buses if they were multi-bit signals by clicking bus and setting the most significant bit to whatever we need it to be. So say Andrew was a 2-bit signal, we'd set the MSB to 1. Since we don't need that for now, we'll uncheck that. Now we also need to put in the output, access granted, and set that to be out. Click OK. And Vivado automatically creates the module Maxis for us in the file maxis.vhd. Alright. Now let me show you a little bit about some of these windows. Whenever we're using Vivado, all of the commands for everything we want to do for putting things on the FPGA will be over here under Project Manager, under Flow Navigator. Now, also, remember in the end of the first Star Wars where Obi-Wan says the source will be with you always? Well, that's also true in Vivado. All of the source will always be with you over here in the Project Manager under the tab Sources, under the tab Hierarchy. So here we have our Maxis module, and if we double click on it, it opens the file. As you can see, it's created our entity description with the inputs and outputs, the architectural description as well. Now from here we can just enter our Boolean equation. AG gets AN and AM, or AN and J, or AM and J. Right. Now we can save that. Now let's say we had a syntax error in here. For example, let's say I forgot the semicolon, and I try to save. Well, you'll notice under Design Sources, there's now a folder that says Syntax Error Files, and Maxis is in it with that little misspelling red under highlight. So that tells us that there's a syntax error somewhere in this file. Now, how can we see what that syntax error is? Well, we can go over to log or messages, and we'll want to take a look at the critical warnings. So uncheck regular warnings and uncheck infos. It says we have a syntax error near end. Not super helpful. Since we don't have the semicolon here, the parser reads this line bleeding into this line and doesn't really discern that the error is actually on line 45, but it gives you a rough idea of where the error is and what you need to fix. So save that, give it a minute to parse it. Lo and behold, we have our Maxis back under design sources. All right. Now, if we want to make sure that this circuit works, one thing that we can do is create a test bench for this circuit and simulate it. But doing a test bench is kind of a tricky thing, so I'll include that in the next video. For now, the first step of getting this circuit onto the board is to first run synthesis. Running synthesis basically allows the tool, in this case vivado, to go through this file and convert this high-level equation into combinational logic blocks and make sure that it can actually make that conversion. So with vivado, this will take a minute or two. Now in the meantime, let's talk constraints. Now we want to simulate this equation on our board, right? So how are we going to toggle Andrew, Amy, and Jen, and how are we going to see access granted? I mean, I'm Andrew, and I'm in no way connected to the board. Access granted is supposed to go to a lock, and I don't have an electronic lock. Well, what we can do instead is map Andrew, Amy, and Jen to some of the switches on your basis board. We can lock access or map access granted to one of the LEDs on the basis board. Now, if we want vivado to do this for us, we have to tell it what mapping we want using something called a constraints file. So, in order to get a nice, easy, pre-populated constraints file, let's go online to the Digilent website, to the basys3 product page, and down at the bottom, we have what's called a basys3 master XDC file for vivado designs. XDC, I believe, stands for Xilinx Design Constraints. Don't quote me on that. But basically, this is a master file of design constraints that has all of the different FPGA pin numbers and tells us what they correspond to in terms of the different peripherals on the basis board. Alright, it looks like synthesis successfully completed. Let's cancel that out for now because we need to add our constraints. So we've downloaded this basys3 master.zip file. Let's show it in folder. And we can extract all. Now I've already done that, so over here I have basys3 master XDC. Okay, so let's add that as a source to our project. Under Project Manager, we click Add Sources. The Add Source menu. We want to add or create constraints. Click Next. Now we want to add that file we just downloaded. So let's go to Andrew Danowitz Downloads, basys3 master, the XDC file. and we will finish. Okay. So now the file's imported, and over here under Sources, the source will be with you always. Check under Constraints, and you'll see basys3 master.xdc. Let's open that up. Now this looks a little scary at first, and for those of you who've seen it before, these constraint files are actually written in the scripting language Tcl, or Tool Command Language, which is a standard language for a lot of tools that we use in industry for digital design. First thing we want to do is set 3 switches to Andrew, Amy, and Jen. So we will uncomment the entries for switch 0, switch 1, and switch 2. Notice that each of these entries are 2 lines. Now that these are uncommented, what we want to do is put in our VHDL signal names. So where it says switch 0, we replace that with Andrew. Alright. Switch 1 is Amy. Switch 2 is Jen. All right. So now on our basis boards, the switch labeled switch 0 will be mapped to the input AN Andrew. We also want to map the output AG to LED 0. So we scroll down to the comment line that says LEDs, and we uncomment these 2 lines corresponding to LED 0, replace LED 0 with our signal name AG. Right. And that's basically all we need to do. To understand what this is doing, though, we can parse this as saying we're telling it as a constraint to set a property package pin, that's the FPGA physical pin, pin number U16, to the port, and then we're using a built-in command get ports on the port AG. Alright. Then we're also setting the property, the input-output standard for this pin, to be low voltage CMOS at 3.3 volts. And we're doing that, instead of doing this directly on a pin, we do it on our signal ports AG. Right. So let's save this, Control S, and continue on with building everything. You'll notice up here it says synthesis is now out of date, because Vivado uses the constraints files in the synthesis. Now that we've modified the constraints by adding some constraints, we have to resynthesize the design. But before we do that, we're also going to set something else in what are called bitstream settings. The bitstream is a file that we're going to put onto the FPGA board itself in order to tell the FPGA how to configure itself to do this circuit functionality. And for the basys3, what we want to do is check this option next to bin file. Write a binary bit file without header.bin. Okay. Right, so we can run synthesis again. After synthesis, we'll need to run implementation. And what implementation does is it takes the results of the synthesis run, all the low-level combinational and sequential logic, and actually maps it onto the FPGA on our basis board and does some timing analysis. And once run implementation is complete, what we'll finally need to do is generate the bitstream so we can program the basis board. Now, since I already know that this should synthesize properly, I can just go ahead and hit generate bitstream, and now it'll prompt me, since synthesis is out of date and there's no implementation, it'll prompt me to run these first, and will automatically generate the bitstream after those two steps are done running. So click yes. Now we get to play the waiting game. While we wait, this is a good time to show you some of the other features of the design tool suite. So down here at the very bottom, we have something called the Tickle console. Remember, Tickle stands for Tool Command Language, which is the language that our constraints are written in. We can also use Tickle to do all of the synthesis and design setup that we've done using the GUI. And in fact, every time we press a command in the GUI, we should see a Tickle command show up here. So for example, launch runs tells it that we're going to be launching some synthesis or implementation runs. And this command says we're going to be doing implementation up to the step write bitstream. So it'll do implementation, bitstream, and all the steps required in between, which is a cool little feature if you're more comfortable with the command line than you are with the GUI. Here we have our messages where we can see warnings. It's generally a good idea to clear all of your warnings, but occasionally we get some spurious warnings such as cannot add, board part, whatever. That just seems to be some sort of issue with Vivado. But if these are the only warnings we have, we're pretty good. Whoop. Looks like we just got 6 more warnings. And again, it's the same cannot add board part. You can just sort of ignore that. Have a bunch of infos. This just tells us things like it took a while to check out a license to use these tools. We aren't using any IP repository, etc., etc. Can add status. But generally, you just care about the warnings, critical warnings, and errors. We can go to the log file. Every time we run a command, it populates the log file with all of the output of, for example, initializing the design for the run implementation step. You can go over to reports, see what reports have been generated so far, double click on them to read them. Design runs. So we've synthesized. Now we're initializing the design for implementation. That's about it for these guys down here. Now up here we have the tabs for the different source files that are open. You can go to one called Project Summary. Now Project Summary is just an overview of everything we've done so far, synthesis, implementation. We got 6 warnings each. We have the FPGA part that we're programming, project name, where it's stored. Then we have some information about how much of the board we're using and the resources we're using. So down here, for example, after synthesis, our circuit uses about 1% of the lookup tables or configurable logic blocks from our FPGA, as well as 4% of the input-output pins. Now, as you can guess from something like this, one of our big constraints on FPGA is our input-output constraints. But that's true on a lot of chip designs. We can put millions of gates on this FPGA, but we only have something like, say, 50, 60 pins that we can use to talk to the outside world. Now eventually, once implementation is complete, there'll be some timing options, as well as, not timing options, there'll be a report on timing, how fast our circuit can run, as well as some power information. How much power does our circuit take to use? Alright, now if we look up here, we can see that we've moved to the right bitstream stage, and we're about 80% done with the full implementation step. And here we are, completely done. So now what we're going to do, in order to actually put this design on our basys3 board, is open the hardware manager and click OK. So connect your basys3 board, make sure that jumper JP2, the power jumper, is set to be powered from USB. Jumper JP1, the mode jumper, is set to the middle two pins, JTAG. Plug the FPGA into your computer through USB, turn the board on, and give Windows a few minutes to install the driver base necessary for this board. Once all that's done, you can come back to Vivado, and now you'll see we have this title Hardware Manager up here, and this green context bar that says No Target is Open, and a link to Open Target. Click on Open Target, select Auto Connect. Okay, so now down here in the Tickle console, you can see that we've connected to our device XC7A35 key. And up here it says there are no debug cores, program device or refresh device. Let's program the device. Select our FPGA. And here we get a window that asks us what we want to program to it. It pre-populates with the bit stream we just generated, maxis.bit, and a debug probe file that we could use to debug things if it came down to it. So hit Program. We'll program the device. And now, on your basys3, you should be able to toggle switches 0 through 2 and get the lock door functionality. So on something like this, where there are only a few test cases, it's generally a good idea to run through all of them to make sure that all test cases work the way you expect on the board. If that is the case, then your circuit is programmed correctly, your circuit works correctly, and you're done. Congratulations, you've just learned how to program your first design on a Basys board. Well, so that's about all we have for today. So thank you for watching, and good luck on the labs.